design. Actually, last year, San Francisco was the first time that I attended this meeting. So it was really wonderful and inspiring to connect with all of you. So when we think about design, I think that's quite broad, right? We could be talking about products, services, systems, and really everything in between. And so actually in our research group at Berkeley, we focus on all sorts of these problems. My area of expertise is called design theory and methodology, as well as design automation. And so today I hope to just give you a little bit of a flavor of what we do and some of the questions that we're investigating. So at least design through my eyes in the mechanical engineering department looks sort of like this, if I could capture in a couple images. So these are pictures from UC Berkeley of our makerspace, where these are students in classes prototyping, trying to bring their ideas to life. Typically, these students are working on projects on teams of 4 or 5 people, maybe with an industry sponsor. You can see them coming up with idea, brainstorming, prototyping, all sorts of things. And so in our undergraduate mechanical engineering design class, this is kind of the flow of the design process that we introduce students to. And so there's 3 main phases: conceptual design, embodiment design, and detailed design. Hope that's okay. All right. And really the work that we do in my lab, and I think the work that's probably most relevant to this community here, is early on in the conceptual design phase, where engineers and designers are defining problems, gathering information. So this is like user research, going out into the field, interviewing people, generating different concepts, and then evaluating and selecting a final design concept. So my lab at UC Berkeley is called the Co-Design Lab, or Cognition and Computation and Design Lab. We look at a lot of problems across how both humans and computers can execute design tasks. And in terms of methodological approaches, we have kind of these 3 main areas. The first are controlled experiments, where we look at both behavioral and computational methods. Systems research, so we'll build interactive prototypes and test them with people. So this can be hardware or software prototypes. And then in the wild studies, where we try and test things out with either professional or student designers. And so super fortunate to have a really wonderful research group of PhD students and postdocs and undergraduate and master's students that cycle in. And we're involved with lots of cool different design institutes and centers at UC Berkeley. So the main ones being the Jacobs Institute, as well as the Berkeley Institute of Design, shown on the right-hand kind of rotating image. This is where my students sit and we do our work. Okay, so really the question that drives us is, how can we empower designers? So what we really want to focus on is how we can better understand some of the fundamental processes that are involved in designer behavior, so that we can help support creative problem solving in design. So I think it's super relevant to this community. Typically, this involves observed or controlled studies and experiments, and a couple different popular focuses in this community. My community of design research would be differences between experts and novices in problem solving, looking at specifically complex, or what we term wicked problems, so things like sustainability, ideation methods, team problem solving, analogical reasoning, and lots more that I could never fit on the slide. And I would be remiss without mentioning the era that we're in now, really fueled by emerging technologies and artificial intelligence that's transforming the landscape of design. So yes, we have kind of this traditional lens of humans interacting in a studio space, but we also have to, welcome in things like extended reality, virtual reality for evaluating design concepts, generative design algorithms shown on the bottom right-hand slide, which can automatically create multiple instances of design alternatives that engineers can decide on during the early stages. And another thing in our approach in my research group is really, how can we go beyond this kind of current paradigm of design? And we do a couple things. And really the crux of it is that we look to understand and combine behavior, cognition, and computation. And so what I want to do for the rest of today really is kind of give you a flavor of some of our past and ongoing work that spans these different topics, and show you how they kind of come together in our research. Before I do this, this isn't my image. This comes from Strathclyde, and I really like this kind of future vision for computer-aided design, right? So if we can imagine sometime, maybe not so far into the distant future, in which engineering designers can use tools without actually having to interface with them, so that we could use, let's say, a computer-aided design software automatically just by the mental representations in your mind, right? And so this is just one representation, I think, of a future lens of design that my research group works towards. How can we enable this? Okay, so the first series of investigations that I want to focus on touch on analogical reasoning in engineering design. So I think this community is probably really well versed in the concept of analogical reasoning. But in terms of how we would think about this in engineering design, so it's been shown many times over the really incredible innovations that can come about by turning to analogical sources. So these are just a couple. On the top is my colleague Hannah Stewart at UC Berkeley. This is a mole crab inspired digging robot. And on the bottom, does anyone know what that is? It's Velcro. Yeah, John, I know that you probably yeah, so this is Velcro inspired by the plants, the cocklebur plants that get stuck onto your leg if you're walking through a field. So we can study not just biological phenomena, but other phenomena we can become inspired by and generate new solutions. So, right, this is very simply the process by which information from a source is applied to a target. And in the application of design, this is interesting because we've shown that analogies can help stimulate additional concepts, as well as concepts that have positive characteristics, such as an increased novelty, feasibility, etc. So there's a lot of open questions that drive me personally. What's the best modality or way to present these analogies to designers? What's the impact of how experienced you are in terms of how you can use this information? And then, as we'll get to in a little bit, what's the mental representation of analogies? Okay, so a couple of different things I need to introduce before we can get into some of the past work. The first is that this idea of distance really, really matters when it comes to an analogical stimuli. So we can think of near or far field analogies being how closely related they are to the problem that you're solving, near sharing mostly surface features with the problem, far mostly non-surface features, for example, the biological examples I showed on the last slide. There's this idea, at least in the design research community, of this quote unquote sweet spot in which analogies are most impactful for engineering designers. And this has actually been shown to be pretty effective if we can find the ones that are not too near to cause fixation and not too far that people don't know how to apply them to the problem. We also know that scale matters. So, I think we can imagine that having not one, but many possible sources to look between would be a really beneficial characteristic. And so looking back, what we started with was the idea that we could maybe turn to the crowd for inspiration. So this is before large language models. There was nothing like that at the time. And we thought, wow, let's see if we can harness other people across a wide scale to help generate potential analogies for us. And so what we did was we identified a common set of design problems. We asked people on the crowd, so hundreds, to solve these problems. We used different techniques of natural language processing to extract what we thought would be useful analogies from this corpus. And then we tested it with engineering designers. So, all right, so here are the 12 and a bonus 13 problems that we selected. So everything from, design a lightweight exercise device that can be used while traveling to an innovative product to froth milk. So a pretty diverse set, and these were things that had been used in the design research community for problem-solving tasks. So we took these, we put them on Amazon Mechanical Turk, which is a popular crowdsourcing platform. We asked these Turkers to solve the problems and to basically just come up with the first idea that they thought of, and then to provide some additional information regarding their solutions. So using this information and natural language processing, what we were doing in the high level is we wanted to find these analogical stimuli at these different zones. So near, far, and we had a third condition that was kind of in the middle. Okay, and so for testing this, we had 4 problems of that original 12 that we selected. We had 111 mechanical engineering students that were in our capstone. So this is like the final year of the undergraduate curriculum design course. And we asked them and randomly distributed which condition they were in. And so, for example, one of the problems was to think of a device to remove the shell from a peanut in areas with no electricity. And so they might have seen this problem with either the near, the medium, the far, or the control words. The control here were just reused words from the problem statement. So across the 111 participants, we collected 1,600 plus solutions. So it's a lot. And for those of you that are doing automatic creativity assessment, it's a good testament to how necessary that kind of research is, even to our community as well. So we had the 1,600 solutions. All of these were scored by expert trained raters that we had. And what we were doing was for each concept, we were trying to assess things like the novelty, feasibility, quality, usefulness of the design solutions. Okay. Right, and at a high level, what did we find? So we found that overall, compared against our control conditions, so this is no analogies, having the near examples improve the usefulness and feasibility of the design solutions, and that the distant stimuli improve the novelty. So I think that for those of you that might have worked on analogical reasoning problems in the past, this isn't maybe too surprising. We were actually quite happy with this because it validated some of the past work in our community, but also showed that this crowdsourcing method and distributed innovation was actually quite effective. The other thing that what showed us some promise was that the categories worked. So among other things, we asked people to rate the relevancy of the different stimuli that they were given to the problem. And we see this nice trend where near, medium, far are rated as kind of more closely related to the problem, but also more useful. Okay, so we had lots of questions, but I just want to highlight one key insight from this work and one key open question. So in terms of key insights, we found that automating analogical reasoning at scale seems possible across a different range or a wide range of problems and people. The key open question that it left us, and for me as a researcher, was what makes this useful in the first place? And so that was kind of my first foray into your community, into neuroimaging, was investigating the neural signatures of design ideation with these stimuli that I just talked about. So this first experiment back in 2018 was an MRI experiment. We had 21 participants. They did a 1-hour brain scan where they saw some variation of the problems. I'll walk you through the experimental protocol in just a second. So basically, when they were in the MRI, what they saw was here. So first they would read the problem. Then they would have a minute of open concept generation where they were presented some combination of the stimuli from our data set. Then they would come back after an intermediate task and repeat another 1-minute problem-solving block where they were shown some additional stimuli. At the end, we asked them to provide kind of the same ratings that we had done previously. And each person here saw 12 different problems. So all of the problems in our data set, randomly distributed. Okay, so in terms of behavioral data, we see that participants generate more ideas in the early part of ideation, and this is irrespective of the condition they're in. So basically the take home here is it doesn't matter if you have any of the inspiration early on, you're going to be doing great and have lots of ideas. In the second period of the ideation process, this is that second 1-minute block, things change quite a bit. And this is where we see that the stimuli have a positive impact. And in particular, those near words seem to be a little bit more impactful for participants. Okay, so I can't go into all the depths here, but in analyzing the brain activity during the design ideation, we found first that there is a, obviously elevated brain activity when participants had indicated that they generated the new ideas. And through analysis, we found these two pathways. The first associated with kind of generating the ideas, having a positive application of the inspirational stimuli, which we linked to areas commonly associated with semantic processing, directing products to internal memory, and solving problems via insight rather than via analysis. We also had a secondary network that we had identified in pattern of brain activation that was more indicative of being at an impasse in problem solving, which we associated with problems that were too far away, and really they weren't able to apply them appropriately to the design prompt. And in a follow-up analysis, we also used, this is more recent, hidden Markov modeling, which is a statistical analysis technique to identify these brain networks and reoccurring states that designers would visit across different problems while solving them. So I promise I would go a little bit fast today, but I would love to have more conversation, obviously, about this in Q&A or in break. Okay, so this was our first neuroimaging study. And again, I like this kind of key insight, key open question model. So here, key insight was really just fundamental new knowledge demonstrating why these inspirational stimuli were impactful for design neurocognition. And kind of the key open question for me as a researcher and for an engineering design researcher was, can we apply some of these insights to quote unquote real systems that might be able to help designers? So that leads me to the second part of this talk, which is our foray into building some of these tools to assist with the inspiration process during early stage design. So the first example of this kind of tool building work that we were doing was trying to provide people relevant examples in real time. Again, this is before large language models, but I think this flow is actually still quite relevant. So for this initial study, what people did was they would solve a design problem. So they'd be on a computer, or they'd be working on desktop, but then they'd have to come back to the computer and provide a written kind of description of what their problem was. Using a large corpus of existing designs and patent data, we would take the text that they provided to us, compare it against that design corpus, bring back a stimulus to them that we calculate as being near or far from what they had, give it to them, let them continue solving the problem, and then they would produce a final design. We evaluated these designs in similar ways to what I showed in the last experiment. And this worked pretty well. And I was pretty happy with this. But there was something that was kind of bothering me at the time, which is this isn't very natural for design work. Designers like to work in much more rich modalities of expression using sketching and CAD models, computer-aided design models, and all sorts of things. And so this is work led by Elisa Kwan, my PhD student in mechanical engineering, and Forrest Wang, who is a former PhD student in electrical engineering and computer sciences. Also in collaboration with Autodesk Research, who's, if you're not familiar, kind of a manufacturer of computer-aided design software used across various industries, from product design to architecture and beyond. Okay, so what were we doing here? It's a lengthy title. So the gist is, what we wanted to do was use an approach called deep learning to retrieve these inspirational design examples across 3 different interaction types. So we let people ask for and request inspiration using semantic search like we had before. But we also had a couple of different ways that they could explore. So one was a form-based search. So using models that took the appearance of either the 3-dimensional model or other objects in our data set and retrieved things that were similar or dissimilar, as well as, and this was the complicated one, the functional search. So I have an object that functions like this. Can I find something else that also functions similarly? And you can imagine if we are doing this for real-time renderings and sketches, it can be pretty complicated. Kind of at the back end of this, if you're curious, we were using an open source data set called PartNet. So if anyone does kind of like computer vision research, you might be familiar with what this data set is. It's a huge open source, 25,000 plus, I think it's even larger than that now, data set of three-dimensional models partitioned into really nice categories of object classes and types, also built upon WordNet, if you're familiar with WordNet. So it's a really rich set of information and data that's structured quite nicely. And so just to kind of put a couple pictures to some of the things I've been talking about, right? So we have this keyword search. Someone could type in something like find me a container, and we would find, you know, the nearest object to that. Then you could search via a part here being a picture of the container, or the actual assembly or structure that they had built up in their three-dimensional workspace. We implemented these sliders that allowed people to toggle between things of low or high similarity in any way that they wanted, both based on appearance as well as based on the functionality of the objects. Okay, and here's a picture. Unfortunately, the video is not playing, but that's okay. So people, you know, could add things into this three-dimensional workspace, and you can see the different search categories available. So we use this for a variety of studies in my group to investigate how engineering designers explore and interact with this really rich set of multimodal design inspiration. You know, and we can do really fun and cool classifications of the, you know, what people are doing. So we can abstract everything into these embedding spaces and look at similarity of things based on the appearance. So these are all objects that designers interacted with. So how, you know, related are they visually? How related are these objects functionally? And so just one example takeaway being that the most diverse examples that people were actually finding is based on that semantic search. So this to us as researchers indicates that when you move to other modalities of expression, like you know, three-dimensional CAD modeling, you kind of fix yourself to that expression. And as a designer, you find a little bit more challenging to then move away from. We also looked at kind of underlying behaviors and cognitive processes as people were searching for these inspirational sources. So we conducted Think Aloud studies. So we had professional and student designers come into the lab, use the tool, solve a design problem, and talk about it as they were going. So this would be a pretty common protocol in engineering design research. And so, for example, here we find that students evaluate more of the results using our tool as being unexpected than professionals, and they also reject more of the search results. So maybe, you know, more experienced designers are perhaps a little bit more accepting of finding these unusual bits of inspiration. You know, some of these being things like, you know, wheels on objects that you wouldn't expect, even though there's no functional relationship between them. They found a way to incorporate little bits of the design into what they were working on. So just one example here. Okay. So again, with kind of this insight takeaway model. So this study was really interesting for us, really because of this multimodal component that I touched on. This was a big challenge, especially at the time for our research group, and something that really hadn't been looked at before. And I think we still have a long ways to go in terms of enabling these really natural to use engineering design tools that can just adapt to someone's workflow regardless of how they want to use them, right? But this insight was regarding the development of this multimodal interface to support receiving inspirational stimuli in design. And it really increased our understanding of behavior and some of the cognitive processes underlying how people are searching for the inspirational sources. Some of the next steps that this left us with, and this is kind of carrying us on into present day, is how else can we better represent relationships between this design information? And really, you know, ultimately, how can design tools be improved based on the way in which people are using them, their behaviors, their cognition. So in terms of representation, tons of stuff. This is just one quick example. We can use generative design, like I showed previously, to just automatically populate new options for people now. And we can also put them in environments like virtual reality to let them explore between different alternatives. So the first example that I just showed was a desktop interface. This one here is a VR interface. So this is just one example. We're trying to push the limits on the representation side. But actually, I think maybe the more active area right now in our group, and what I think is perhaps a more pressing problem, has to do with this alignment issue. So how do we align the way that computational models are operating and behaving to people's behavior, as well as their, the way that they're thinking about it? So just thinking about kind of the problem here, you can imagine, right, as I've described, all of these tasks involve, I have a thing, I need to map this thing, text, image, whatever, into some space and compare it against other examples that I have available to me. And so, there's different techniques that we can use to do these calculations, right? So we tested some of the most common similarity metrics that are used for these tasks. There's vector-based metrics, there's network-based metrics. And the high-level takeaway here is that the choice of metric matters a ton. So we can feed in the same, so that what you're seeing on the left is a functional decomposition of a wind turbine blade. So this functional decomposition is common in design. We're looking at all of the component parts for a high-level system. And when we feed in this design into the system using the different techniques, we're getting wildly different results. And typically as a researcher, this choice between method is typically just you pick one and you go with it. But if someone was using a tool of ours and we had chosen this one compared to this one, they would have a very different end result. We also then naturally became curious, what about how humans think about similarity, and how does that compare to the way that our computational systems are computing similarity? And so basically the approach here was we picked, a ton of different objects ranging from toys to kind of like office products, all sorts of things that were in an open source data set that's available to researchers. And we asked people to evaluate similarity between these objects based on its functionality or other characteristics of them. And we compared that result to different computational models. What we see is that similarity judgments by humans only match those by the computed measures like half of the time, basically. So not very good, and I think a long way to go here. And we've continued to kind of probe this question, with different types of stimuli that we're looking at, as well as different approaches to calculate similarity, both on the human side as well as what we're calling the psychological side. And even now, if you come to our poster on Friday, you can look at some work relating to alignment between brains and large language models, which is another kind of thing that came out of interaction with this community. So, okay, I'm just going to wrap up now. Really today was about showing you a flavor of research and engineering design that I think might be interesting. There's so much possibility for cross-pollination between the design research community and the creativity community. And I think we have a lot to learn from one another and a lot that we can share with each other. I know for me as a design researcher, our work has really been amplified by the interactions that I've had with you. And I hope at the very least that you might view design as an interesting test bed for some of the problems that you're working on. As we look into the future, I think that there's an opportunity to combine behavior, cognition, and computation to really enable some really interesting solutions that weren't possible before. And some last kind of final thoughts, and this is a mix of thoughts and open challenges. So things like, what are good sources for us of data? especially like human-centered data, so data from people, as well as good problems, right? So this problem debate is one that is very common in engineering design as well. Are we picking the right problems for people to work on? Should we all be using a common set of problems? This idea of real-time monitoring and evaluation of design concepts is super important. So how can we in real time assess, say, the quality of someone's concept or a characteristic of a concept or idea? How can we then use that information to act upon it? So I call this targeted reorientation within a solution space. So I've represented something about the problem. I want to take that into a larger space and do something. Show them another example, change what that input design is in some way. And how can we on the fly adjust and define these goals? And then I think, the role of different interaction modalities, I showed you a snippet of this, but it's a really, really hard problem. So the flexibility and how this changes across different stages of the design process. And then finally, improving this alignment between people's behavior, what they're doing, the way that they're thinking, as well as the computational tools that they're using. So with that, love to take some questions. If you don't ask a question, but you want to reach me, any of the coordinates here to see either reach me or see kind of what our group is up to at Berkeley. Thanks so much.
Thank you so much, Kosa, for this fantastic presentation. And hopefully we'll continue asking questions and discussing all of these topics throughout the day. We will open up the floor for questions for Kosa. Please remember to come and ask your question in the microphone.
Incredible talk. Thank you very much. So just one question that came to my mind, listening to the talks about constraints, which is an idea that we often think about in creativity. I wonder how that translates for you guys.
Great question. So it's about constraints, and it's something that we think of quite a lot. Typically, when I'm thinking about constraints, it's something that we build into the design brief or the design problem that people are working on. So in some of the examples that I showed you, there are kind of these implicit constraints, right? So like the peanut sheller problem, it says that you're in a low resource setting. So that implies that you might not have access to maybe modern technology for the solution. But those are simple examples. I think for other problems that we're working on, the constraints can be much more explicit in terms of strength to weight ratio requirements, material requirements, manufacturing requirements. So it's super important. I will say, though, I think for a lot of the kind of like creativity and open-ended problems that we have been working on, they usually don't have many constraints compared to a typical, let's say, engineering design project that might even appear in one of my courses.
I have a question actually. The alignment results you shared were fascinating. And if I recall, the 57% only agreement, what do you think humans are doing different?
I was hoping you could tell me the answer to this. Yeah. I think we really don't know is the answer, unfortunately. I think one of the biggest challenges is actually going back to this like constraints question, has to do with the information that humans are quote unquote prompted with. And so now that we've been doing the large language model work, we're seeing this even more and more, right? So for those of you that have interacted with a large language model, you know that what comes back from the language model is incredibly sensitive to how you prompt the model. So really slight variations in that input parameters can have profound impacts on what comes out. I think humans are the same way. So how we show information to people, the environment that they're in when they receive that information, the wording, the piece of paper, all of this, the screen that they use, I think it matters for how they interpret the information, how they use it, and how they think about the problem. And typically as researchers, we're not controlling for really any of that, if I'm being honest. So I really think we need to think deeply and carefully about the ways in which, you know, we are presenting information to people, all the way down to the context of the room, the time of day, like the state that they enter the research laboratory in, because it has an impact on problem solving.
Good morning. Thank you very much. I'm just wondering how metaphor is used in design thinking. You didn't mention it in the presentation.
Maybe can you expand on the question regarding metaphor?
Well, it's an implied comparison. Two things. Their eyes were like the sun. So it stretches the imaginative comparison of one thing to another.
Sure.
And there are references to cars, you know, the car is like a panther or a cheetah.
Yeah, sure. You know, to be honest, you know, studying metaphor usage, at least for me, has not been particularly popular. People, of course, mention metaphor usage in design, and if you, you know, and some of the behavioral studies that I didn't mention, especially these like think aloud protocols, or if you are asking people to describe their design work, they will commonly use metaphor to both describe past ideas as well as to think about alternative solutions to problems. For whatever reason, I personally have converged more on this concept of analogical reasoning in design, which is quite related to metaphor usage and production. And it's like, they're cousins.
Metaphor is a little more of a
Right. Part of that reason just comes from, you know, linking into some of the bio-inspired design community, which is quite popular, which really hinges on, you know, analogical reasoning as kind of its underpinning. But yes, metaphor definitely does come up, and happy to continue the conversation. I know there's some other design researchers here as well that would definitely do more work on metaphor than I do.
It's close to my heart. I'm a writer, of course.
Yeah.
Metaphors are, you know, my bread and butter.
Absolutely.
Thanks.
Yep.
Thank you again for a very interesting talk. I want to raise a question which has sort of been alluded to, and that's about measuring creativity.
Sure.
Here we are. This is a society which has the word creativity. Its title, you mentioned creativity, and we all work in this area somehow. Yet we have no fundamental agreement as to how to measure it. We see things like the gold standard, it's Amabel's essential assessment technique. When you apply that, if that's our gold standard, we're in real trouble. And so I have two issues here. One is maybe our notion of creativity is sort of too impoverished. For some reason, psychologists, and I presume that is a lot of people here, or not. I hope it is, because I want to say something bad about psychologists. Have thought that novelty and utility are these measures which then give you entree into creativity. And, you know, that's really a fundamentally weak claim. And this is not the time to rehearse why it's weak. It's very easy to demonstrate why it's weak. If that's the best we can do, I think we're going to have a lot of issues ahead of us. So, creativity is clearly a social construction for a start. It isn't sitting up there, it's just what we decide. Do you have any insights, having tried to apply these various techniques for measuring what is claimed to be creativity, as to where we could go, not where we've been?
Wow, that's a tough one. I think you maybe partially answered the question yourself, John, in terms of a call for action. when I think about creativity, at least for the work that I do and the way I, want to kind of promote creativity within my own research group, is thinking about the context in which it's creative. So creative to who and for what? It's really context dependent, depends on the problem, depends on the situation. Typically in engineering design, we're assessing creativity relative to a set of other designs, whether that's the past design examples for that domain or that problem, or maybe a larger set. There's a lot of different ways that we can assess creativity, and they don't align very well. And there's some work that shows, creativity metrics between our, the two communities here today, mostly in terms of your own and then design research, aren't well aligned. So I think we have a long way to go there. But for me personally, creativity is defined in terms of the context that we're designing within.
Thank you so much. And we'll continue this discussion at the end of the day. I think we have time for one more question for our virtual audience. Or is there anyone from the virtual audience? No? Okay, so maybe that's been a great place to stop. Thank you again, Kosa, for this great